Now that we know the new operator of gradient, let's tie together the concept of the electric field and the potential. The main thing I want you to be able to do at the end of this is, if I give you one, to know how to go to the other. Let's start with the concept that we introduced first. We had discussed that the potential V will be equal to minus the starting position and the ending position of E dot dl. Or in other words, it's F dot dl, or the work performed to move a charge from the initial position to the final position, but you divide out the Q so that it's a matter of the amount of work that you would perform per unit charge. Now that we know the gradient operator, we can do the opposite, so go from the E field to the potential. The E field in this case is negative the gradient of V. So these are the two relations that let you go from one to the other. I think that the key thing to remember is still going back to that analogy that we had of elevation and the respective slopes. So remember, and also the analogy that we have of moving from a lower point to a higher point in a gravitational field mg, and doing work which then turns into potential energy. So this is the same thing. When you're calculating the potential, it's equivalent of how much energy is stored by getting the charges to where they are. So if this was the ground, to move it up, that amount of energy is what we call potential. And if you have this amount of potential, the corresponding electric field would be negative of the gradient. Now, the negative sign, if you were to follow our elevation analogy, remember we had talked about how if this was a mountain, where this is the peak of the mountain, this is the isoplane of, again, 1,000 meters, 800 meters, 400 meters. The gradient is going to be the field of vectors that tell you how uphill things are. So if it's really steep, you'd have long arrows at a location, and if it's not so steep, you would have shorter arrows. And this negative sign means that, remember, I mentioned that the operator of the gradient gives you the uphill arrows, right? The electric field is the force that you occur when you cash in what the charge experiences when you move from a higher potential state to a lower potential state. So it's more analogous to the force that a boulder would experience rolling downhill. So what you want are downhill arrows, and that's what the negative sign is. So I'm not introducing as many new concepts. Now that we've introduced the gradient, I wanted to provide this new solution that allows us to relate the electric field to the potential. And now that we can move between these two, we can also use one to calculate the other. So if you are given a potential field, you can now use this operator to calculate the corresponding electric field that matches this, and also vice versa. If you're given an electric field, you can now calculate the potential. Now that we have this basic relationship, let's look at how we calculate the potential for three kinds of situations. One is a point charge. And next up, once you have a point charge, you can also do integrals to develop line or surface or volume charges. And that's something that we've done for the electric field in prior chapters. And then separately also introduce the concept of the dipole. So let me clean this up and we'll start tackling these one at a time. To clear that up, first off, let's look at the point charge. One concept that I like to introduce is that if all you have in your system is a point charge, then the energy in the system is the reference. You need a reference to calculate the potential, and the reference that we typically use is to bring that charge in from infinitely far away. So from R goes to infinity all the way up to where the charge is. And so what you're kind of saying is that in an empty universe with this charge infinitely far away, the energy in a system of charges is if you just brought these charges in from infinitely far away and then assembled them 1 point charge at a time. That gives you the value of the potential for a given system in the most basic sense. And then separately, if in the future you might have a different point that you want to use as your reference, but absent of that, if you just have a bunch of point charges with no further information, your reference point is r goes to infinity. Now let's recall that the electric field due to a point charge is q over 4 pi. And then let's just make our lives a little bit easier. We'll say the charge is sitting at the origin. So what we're saying is that this is the origin here, and so r prime, so actually I should say r prime is going to be equal to 0, and we are looking for the electric field or the potential at any point from the origin. So r is the point that we're observing, and then r prime in this case is equal to 0. Therefore, to find the expression for the potential, v of r, we would take the negative integral of, we go from infinity to the origin of the charge q over 4 pi epsilon r minus r prime d r prime, and this is just as a reminder, this is the charge, right? So we're bringing it from infinity to 0, and this is squared here. And if you take this integral, you're going to find that in the most basic situation where, this reduces to power of 1, the negative signs cancel, and we're left with q over 4 pi epsilon r. So this is the equation for a basic point charge. If we have that, we can then extend that to a line, surface, or a volume charge by using our ability to do line, surface, or volume integrals to combine a bunch of r primes. Right? So we have, for the purposes of volume integral, we could have v of r is going to be equal to the triple integral of rho v of r prime all over 4 pi epsilon of r minus r prime dv. So you're going to integrate over the course of that entire volume, where r prime is the location of all the charges. So you're going to substitute in values for r prime as you're doing this integral over the volume, and then you're going to be left with a function of r. In the case, so this is the volume. In the case of a surface, you would do the same thing. So v of r is going to be equal to the double integral of rho s. This is now a surface charge density, but otherwise your process would stay the same. So r minus r prime, and then you're integrating it across ds. And a line integral, our new foe, is the same thing. So v of r is going to be equal to an integral of rho l r prime all over 4 pi epsilon r minus r prime. But here we're just doing a line integral. This formula for using charges to find the electric field means that there are now two ways to find v. One is the original way that we introduced is if you have the E field, you take the integral of E dl. But then now we also have this new approach where if you know what the charge density is, you can then treat the charge density as point charges and integrate your way. V of r is going to be equal to some kind of charge over 4 pi epsilon and then dv or s or l. So you can do that so again, if you're given the electric field, you can take the integral to find the potential, but this approach, this set of formulas here gives you another way of finding the potential directly from the charge. And that, once you have that, you can also just do the gradient to find the electric field. And indeed, that's one of the common ways that we would use to find the electric field. Is usually what you have is often you're given the charge, and so you can use the charge to numerically find out what the potential is everywhere, and then again you simply take the gradient to find the electric field. Finally, before we wrap up, I also want to introduce the concept of a dipole and make sure that you're aware of what they are and the general formula. Usually, a dipole consists of a positive and a negative charge. For the purposes of our calculation, we'll put the origin in the middle. And this will be Q, this will be minus Q. This is a very, very basic element that we use to describe a lot of things. You might be more familiar with a magnetic dipole, where you have a north pole here and a south pole here, and the field lines would look the same as what you would expect in the case of a magnet. Right? It goes from the positive to the negative in this kind of fashion, where it kind of radiates out as you go along in this way. And one key description of the dipole is what we call the moment. So the dipole moment will be the vector that I'm describing here, which is the distance between these two charges and the value of the equal and opposite charge. So QD. Using this notation, so first of all, I want you to be familiar with the notation of how we describe a dipole. We can often describe it by using a vector coupling with a location. And I don't think the derivation is too terribly important at this point. What I really want you to be able to do is to just have access to the formula that describes the potential in the electric field, because as I mentioned before, this is a kind of a basic element that you use to solve more complicated problems. So for those of you that are using the Hayt and Buck textbook, the section 4.7 has the derivation, but the potential turns out to be equal to QD, again, this is if it's at the origin, QD cosine theta 4 pi epsilon r squared, and the electric field is going to be equal to QD over 4 pi epsilon r cubed 2 cosine theta r hat plus sine theta theta hat. So again, the main take-homes at this stage is to make sure you know what these two equations are, because we use them as basic elements to talk about other things, and also know what a dipole is. So two equal and opposite charges, and you define the dipole moment as a vector that goes from the negative to the positive, and it's proportional to both the distance and the value of the charge. So in summary, we talked about the general formula of using an integral and a gradient to go both ways, from an E field to a V field and vice versa. And also using the basic equations, we highlighted how to calculate the potential for a point charge, and then expanding that to how to calculate it for charge density, and using integrals to find the potential for a line, surface, or volume charge, and then introduce the concept of a dipole.